The interquartile range, which is going to be abbreviated IQR, is the range of the middle 50% of the observations in the data set. The interquartile range is another measure of dispersion that we can use. So we had the range, if you'll remember. The range was the largest value minus the smallest value. The trouble with the range was it was not resistant. The interquartile range is a similar kind of measure as the range, except it's taking the third quartile minus the first quartile. So it's resistant. It's not going to be affected by extreme values. And it gives us a measure of how spread out the middle half of the data are. So 50% of the data will be between the first quartile and the third quartile. So between here and here is 50% of the data. And so if I take this value minus this value, it gives me the range of the middle 50% of the data. And that's what this is saying. That is, the interquartile range is the difference between the third and first quartiles and is found by using the formula interquartile range equals Q3 minus Q1. So example, using the smart car data from the previous example, compute and interpret the interquartile range. So if I go back to my previous example, and I'm using the original data with the 47.5 included. So I'm going to unscratch that, right? That's included. So these were my quartiles. So my interquartile range for the smart car data is going to be 41, the third quartile, minus 36.85, the first quartile. And so if I do that, 41 minus 36.85, that is 4.15. So the interquartile range is 4.15. There are units on that. That would be miles per gallon. Now, where does this come in to use? Well, we've talked previously about extreme observations, extreme values in our data. And we've talked about the fact that when we have extreme values in our data, they can cause problems for us. They can cause problems with the calculation of the mean, right? The mean's affected by extreme values. Standard deviation actually is too. So we would like to identify extreme values. The question is, how do we do that? Look back here at the smart car data. 31.5 is quite a bit smaller than the next smallest value, right? 31.5 compared to 34.3, that's nearly a 3 mile per gallon difference. Is 31.5 an extreme? How about 47.5? 47.5 is the highest value. Is that an extreme? The point is, it's kind of debatable, right? Now, if I had 57.5, I don't think anybody could argue that wouldn't be extreme. 47.5 is maybe a little debatable. Yeah, it's the biggest value, but is it so big that we would call it an extreme? Maybe. And the same with the 31.5. Maybe that's an extreme, maybe it's not. So what we would like to do is we would like to come up with a way to define it so that everybody can agree. Yes, this meets the standard to be an extreme, or no, it doesn't meet a standard to be called an extreme. So it's not up for debate. It either fits the standard or it doesn't fit the standard. So that's what we're going to be looking at next. We have this term outliers. So an outlier is an extreme observation. It's an extreme data value that occurs in our set of data. So we're going to determine if data values are outliers or not. So we have some rules. First of all, the way we're going to calculate outliers is this right here. This is the most important part. We're going to calculate what are called fences. We're going to find the lower fence. We're going to find an upper fence. So fences is going to be like the boundaries that's going to separate outliers from not outliers. So the way we're going to calculate the lower fence is we're going to take the first quartile and we're going to subtract 1.5 times the interquartile range. That gives us, again, this lower fence. It's a boundary. Any data values that are below the lower fence is an outlier. In the same way, we're going to calculate an upper fence. So to find the upper fence, we're going to take the third quartile and we're going to add 1.5 times the interquartile range. So any data value that's above the upper fence is an outlier. So these are giving us boundaries for what's an outlier versus what's not an outlier. So we're going to find the first and third quartiles, which we've already done in the previous step. We're going to find the interquartile range, which we've already done in the previous example. And we're going to determine the fences. So we'll have to calculate the fences. If a data value is less than the lower fence or greater than the upper fence, it's an outlier. So my next example, using the smart car data from the previous examples, determine the lower and upper fences. Are there any outliers? And if they are, what are they? So in my previous examples, we found Q1 to equal 36.85. We don't need it for this, but I'm going to go ahead and write it down. Q2 was 38.35, and we found Q3 to be 41. And we've already calculated in the previous example, the interquartile range is 4.15 miles per gallon. So all I did was I rewrote what we found in the previous problems, the first quartile, the third quartile, and the interquartile range we found. So I'm going to find my lower fence. My lower fence is going to equal the first quartile, 36.85, minus 1.5 times the interquartile range, which is 4.15. So if I do that calculation, 36.85 minus 1.5 times 4.15, that is 30.625. So any data value that is smaller than 30.625 is an outlier. I'm going to now find my upper fence. My upper fence is the third quartile, that's 41, plus 1.5 times the interquartile range. So if I take 41 plus 1.5 times 4.15, that is 47.225. Any data value larger than 47.225 is an outlier. If a data value hits the fence, right? This says if a data value is less than the lower fence, doesn't say anything about equals, right? Or greater than the upper fence, doesn't say anything about equals. It's considered an outlier. So if a data value equals the fence, it's not an outlier. It's got to be below the lower fence or above the upper fence. So I've calculated my two fences, and now are there any outliers? Well, looking back at the data, our smallest data value is 31.5, and that is not below the lower fence. So we do not have any outliers on the low end. Our largest data value is 47.5. Our upper fence is 47.225. That 47.5 is above the upper fence. So the 47.5 is an outlier. It is possible to have more than one outlier. So you could have a couple of values that are above the upper fence or below the lower fence. You could have outliers on both ends. You could have lower outliers and upper outliers both. You could have multiple outliers on either end. One purpose for finding outliers is that oftentimes if you find an outlier, it could be that it's a data entry mistake. Like for example, maybe somebody goofed up. Maybe that 47.5 was supposed to be 41.5 or 42.5, but whoever wrote it down wrote it messy, and whoever read it next misinterpreted. It was supposed to be 41.5, but they thought the 1 was a 7. So when we find an outlier, the first thing that we should really do is investigate to decide, is that a legitimate data value, or is it a value that needs to be corrected? If it needs to be corrected, well, correct it. It may also be that it's a legitimate data value. And so if it's a legitimate data value, then we have to make a tougher decision. What do we do about it? So this is kind of an anomaly, right? It's not typical for the smart car to get this good of gas mileage. So what do I do? If I'm going to calculate the mean and the standard deviation and so on, do I leave this data value here, knowing that that data value is going to skew the calculations, or do I make a more challenging decision to remove that data value from my data? If I know that it's going to skew the calculations, then I might be able, as an expert in my field, to argue that's an anomaly. And so therefore, if I'm trying to summarize what happens normally, then maybe I would argue to remove that data value from the set. Now, if you do that, if you decide to remove a data value from the set, you should be ethical about it and report that you've done so.